Okay, let us begin. I didn't finish grading quiz 7, but just a couple things, not huge things. So, prove something like, I don't know, A union B equals C. This is just some random examples. What do you need to show?
A union of subset C. C is a subset.
Okay, yeah. And how do you show that?
Show that if X is an element of A and B, it is also an element of C and vice versa.
Right, so the first time I saw it, I figured it was like a typo, but I didn't finish grading the quizzes, but I still found like a handful of people who did this. You neglected to write this part. I don't know what that's about, if that's like a conceptual thing or you guys just forgot, but a lot of people did it. So some people would be like, assume A union B, and then they went on to the proof. What does that even mean? Assume A union B. You know, the X is an element of it, actually a pretty important part of it. Just to mention that. I don't know if there's something, because it happened too often to be a typo, I think. So I just want to make sure that you guys understand what this means. There was another question. It said, A is an irrational number, R not equals 0 is the rational number, S is just a random real number, then the R plus S or the R minus S is irrational. How do you prove that? A lot of people seem to be messing up on that so far. Give me some ideas.
Assume that A, well, you assume the first line. And then assume that both of them are equal to rational numbers.
Okay, so let's do that part. So I guess you want to do like a contrapositive or a contradiction. Like those would both start out the same way, right? So you can assume AR plus S and AR minus S are rational numbers. Now, the first mistake that was quite common here is several people assumed they were the same rational number. They were like AR plus S is P over Q and AR minus S is P over Q. That is, of course, the first mistake, right? In general, these two numbers will not be equal, right? If you add an S or you subtract an S, it won't be the same thing. I saw that a few times so far. That cannot work, right? You'd have to assume they're different, like N over M or something like that, where P, Q, N, M are integers with Q and M not equal to 0. Okay? So the first mistake was people assumed they were the same thing. Like, let them both be A over B. You can't do that, right? They're not. In general, they won't be the same. And then what would you do here?
Add the two statements.
Right, so to me, and so far I've been grading, and a lot of people did not try to do this, but I figured like adding the two would be the thing to do, right? So you add these two equations and you just have 2AR is equal to P over Q plus N over M. And this is obviously a rational number on the right side because you're just adding two rational numbers, but the problem is this side here is actually irrational because A is irrational. And we proved earlier that, an irrational times a rational will be irrational. So this leads to a contradiction here. Right? So far as I'm seeing, very few people actually did something like that. And the people who did something like that, they actually assumed these were the same. So just want to make sure you know. You can't really assume these are the same in general, unless you know for a fact that S is 0. Can anyone think of another way? Another mistake was some people assumed they assumed A plus S or A R minus S are rational. What's wrong with that statement? It's not a contrapositive. Why? Because the negation of or is and, right? So if you assume one or the other, you're not assuming the negation, and in fact you're begging the question. If you're assuming one or the other is rational, it means one could be irrational, which is what you have to prove. Right? So that was another mistake. Forgetting to change or to and. I saw that a couple times so far. Can you tell me another way to try this? Some people tried another way. What's another way to do this?
Well, I think what I did was I assumed both were rational, and then what I did was two cases, if S is rational and S is irrational.
Oh, you did, okay. Alright, so you assume AR plus S. Did you actually write these as fractions or no?
Yeah.
Okay, so assume this is P over Q. AR minus S is N over M. And then you did cases. So you said either S is irrational or S is rational. Okay. And in case 1, what happened?
I didn't finish.
You didn't finish? Could you make this work? How would that work? Where would you go from there?
Well, I guess the second case is pretty easy because then you just are adding and subtracting a rational number from a rational number.
Right, so if you look at case 2, right, if you assume S is actually rational, then that means you can write AR as N over M. Where am I? Okay, here. N over M plus, let's say I was looking at this one, plus S, right? Which would mean if S is rational, then this would be rational, right? Which is a contradiction. And similarly here, you'd have AR equals P over Q minus S, which would be rational. And that would lead to also a contradiction, right? Because we know that A is irrational. And so in case 2, you get a contradiction, so it means we must be in case 1. And what can you do with case 1?
So that one you can kind of break up into 2 separate cases again. Which is like if you look at AR plus S.
Okay, so look at AR plus S.
So if
then we're assuming S is actually a rational number.
irrational,
We're assuming S is irrational. Okay, so we have this. What do you say?
So what do you have to assume that S is irrational? You do like contract contradiction, you assume that A is rational, R is rational, S is rational, and AR plus S.
We know A is irrational.
And you know that S is rational. On top there.
Oh, that was in this case, which we're done with now.
No, look at your test comes out, A is irrational, R is rational, S is rational, then,
No, S is real.
oh, real, okay.
Yeah. It could be rational or irrational.
Yeah.
It's just a real number. On the case where it's rational, didn't make any sense, right?
Mhm.
And so now I'm assuming it's an irrational number.
But why would you express S as n over n, then AR minus n over n, and plug it in instead of there?
What if you did that here? So S would be, in this case, P over Q minus AR. And then you would plug this in to the other equation.
Uh-huh.
So the other
It's
equation
like the
was
same thing, just adding.
this one.
Yeah.
So you have AR minus S, which would be P over Q minus AR, equals N over N. Well, I have N over N. So what would happen here, this would be 2AR would end up being equal to N over N plus P over Q, which is rational, which leads to a contradiction. So that way could also work. Right, so if you had time to finish it, hopefully you would have something like that. Can you think of another way?
Okay, so if it is this way, then you can show case one.
What about case one?
Like the person that S is rational or S is irrational, because like in S we actually don't care about what it is.
Yeah, it actually wouldn't matter if that S is irrational or rational.
Yeah, it's like the same thing as.
Yeah, like you could have skipped these two cases and then just did this. Yeah. And the other way that you could have done this, which will probably also end up being similar to this, is you can assume one of them, like say, assume AR plus S is rational. Then AR plus S is equal to P over Q. For PQ is AQ not equal to 0. Then what could you say? Again, you could probably continue similar to this. S equals P over Q minus AR. And this would mean AR minus S would be equal to, how do you continue this one, this blank answer?
Well, it'll be equal to some integer x, or not integer, sorry, some number x, right? And by just plugging in for s, you can prove that x is going to be an irrational number, since r is, since a is irrational.
So you're going to prove that what?
So, I guess really just plug in for s, you can show that.
Well, if you plug in for S, what would happen?
Then you get
Q minus AR. Then you get 2AR minus P over Q.
So then it's going to be irrational because you're adding a
Right.
rational number.
So this is clearly this, since 2AR is an irrational number and P over Q is a rational number. And we know if you does that work though?
If you take that, we've already shown that irrational plus irrational is irrational, which is true.
Irrational plus
As long as,
irrational. Yeah.
since r is not 0.
Since R is not 0. Why does this line of reasoning work? Why can I assume this is rational and then do this? Why is this a valid assumption?
Well, because that's essentially like taking the case. Because irrational, then that's like the question. So this is like starting from.
Similarly, in general, but why is it okay? Why is it okay to prove, let's say, P or Q fulfill property X, to assume P does not fulfill property X, then show Q fulfills it. Right? So I want to say P or Q is irrational, right? And what I did was assume P is actually rational, which means it doesn't fulfill this property, and show that Q fulfills that property. Why is that okay?
If this is for showing this one number is true, so we can assume the number is false, but if we true that one of them is true, that's a false statement is true.
Yeah, that's one way, right? So if you just prove that any one is true, that's okay. But would it make a difference if I assumed Q was false and showed P true? No, it wouldn't make a difference. In general, does it matter which one you pick? Well, in general it wouldn't, but I guess it would depend on what P and Q are, which one is more accessible. But one reason why it's okay is because of what I mentioned last time, is you can actually break things into two cases. You can think of P fulfills X or P doesn't. Right? It's always okay to assume this, right? Because we know that P or not, the negation of a statement or the statement itself is always a tautology. If it fulfills X, then you're done. There's nothing to prove. So they usually don't even mention this case, and they just say, pretend it doesn't fulfill it. And then you show the other one fulfills it. And then that's okay, right? So implicit in this, you could have said either AR plus S is irrational, or AR plus S is rational. In this case, we're done, right? There's nothing to show. So assume this case, and that's where the proof starts, right? They really don't have to say that because there's really no point.
So this is really like a direct proof, essentially?
It's sort of like it would be a direct proof, yeah. So this is a general technique. It's useful sometimes if you want to prove something or something fulfills a property. Just assume one thing does not fulfill a property and show the other one does. That's just for future advice. I mean, sometimes, it's obvious that one way might seem easier than the other way, but you really want to practice knowing different ways how to do things, right? You really want to train yourself to be flexible in your thinking and stop just thinking in one way. It's pretty good practice that when you're proving something, try to prove it in more than one way, right? It will help you out later. So let us continue with chapter 6. Oh, and by the way, homework 6 and 7 due tomorrow. Whether I finish chapter 7 today or not, it doesn't matter. Do the homework, do it tomorrow. Because in chapter 7, I'm not going to teach any new techniques. It's just sort of, it's stuff you can figure out if you think a little bit. The problems actually aren't that bad. We'll talk about it a little bit, I guess. But let's continue with chapter 6. I at least want you to start practicing on that. And there aren't a lot of problems in chapter 7 anyway. Let's see. actually proved this before, I think the first day. Let's now prove it using induction. What would an induction proof to this look like? The size of the power set is always 2 to the n for any finite set n, A. The base case? Right, which is n is 0, right? So if n is 0, what is A? If A is the empty set, this means the size of A is 0. It's the only set with the size of 0. And the power set of A would be what set? Just the set of containing the empty set, which means that the size of the power set is 1, which is 2 to the 0. Right? So the base case checks out, right? When n is 0, the size of the power set is 2 to the 0. Now assume Kn holds. We show Kn plus 1. How? How do you show Kn plus 1?
So we want to show that P of A for A is equal to n plus 1 is equal to 2 to the n plus 1.
Right, that's what we want to show.
So we're going to say that it's twice 2n.
Let's start out that way. So basically I want to show that the size of the power set of B is 2 to the n plus 1. Right? How do I do that?
So we can use it rigorous enough to say that since B is equal to the union of A and the element A sub n plus 1, then the power set will contain the power set for A by itself, plus all of the elements of the power set with A sub n plus 1 added.
Yes, that is rigorous because of what we can say here. Note there are 2 cases for every x in the power set of B. 1, either an plus 1 is an element of an plus 1 is an element of x, or 2, an plus 1 is not an element of x. So in this case, x is just a member of this guy, and we know this guy is 2 to the n. And in this case, we will also have 2 to the n Right, so we basically say there are two kinds of subsets, the ones that don't have this new element and the ones that do, right? The ones that don't have it, we know there are 2 to the n of them. And then we just take those same guys and we throw in the new element in them to get another copy of the subsets. So this means the total number of subsets is just 2 to the n plus 2 to the n equals 2 to the n plus 1. Here's another example where we can use a neat trick that I want to show you guys. We'll use the intersection. How do we prove that? The generalization of one of De Morgan's laws. So clearly A1 is equal to A1. So that works out. Technically doing this way is a strong form, which we'll talk about later. What about two cases? So now assume P of n equals So now I'm taking the complement of the intersection of n plus 1 sets. What can you make this look like?
Can you say, for example, that A without a subscript equals to A1 and A2 until the AN? So we will have the, yeah, A.
Right, so the trick here is to realize that the intersection of a bunch of sets is just another set. Right?
And then
So if I rewrite this as that, then what do we have?
and then by the Morgan's law.
Again, by De Morgan's law, we have A union AN plus 1. But that's just equal to, this guy is just A1 union A2 union all the way up to AN union AN plus 1 by the inductive hypothesis. Right? So the thing is here, A would have n elements in it, which means that since Pn holds, I can actually break up A like this, and then we automatically get Pn plus 1 holds. So that's just a trick that comes in handy sometimes. You can actually replace a bunch of things with one thing. There are a couple of the homework problems where doing that will be useful. And just apply your rule to two things, because we know it applies for at least two. Let's do this one. 2 to the n greater than n squared, or n greater than or equal to 5. So there's the principle of math induction, and then there's the generalized principle of math induction, which basically means your base case doesn't have to be 1. You can prove pretty easily that it's okay if you start at some later point and then continue forever. And pretty much goes the way you expect, right? So you prove it for the base case, except now your base case isn't 1, it's just a higher integer. So proof. Pn is the statement, 2 to the n is greater than n squared for all n. Greater than or equal to 5. The base case now is just the n equals 5 case. And so what we'll do is we have 2 to the 5 is greater than, just write out 2 to the 5 is actually 32, which is greater than 25, which is 5 squared. So the base case holds. Assume Pn holds for some n greater than 5. Then we need to show, what do we need to show? 2 to the n plus 1 must be
Or
greater than n plus 1 squared. Okay, how do we show that?
You can start from what you have to n is greater than n squared, and then multiply by 2. Both sides.
So, but 2 to the n is greater than n squared by the inductive hypothesis. This means you multiply both sides by 2. Okay, now we continue.
We can break up n squared plus n squared, and then we can say that
N squared plus n squared.
n squared is bigger than 2n. Can we substitute instead of n squared plus n squared? Can you write n squared plus 2n?
Since that's greater than 5. Greater
Okay, but with 2n help.
than 1 plus 1.
Two n wouldn't help because I'm going to want the n squared plus 2n plus 1. And if I just put a 2n here, adding a 1 is going to be a problem.
No, the right is so 2n is bigger than n squared, but then put the x bigger than 2n because 2n is not equal to n squared, and 2n to the n is bigger than 1. If you open the parentheses for n plus 1 squared, we can just
Yeah, I know that this is what I want to show, n squared plus 2n plus 1. So if I just replace this with 2n, which I could, then adding this 1, how do I know that this will still be bigger? There's something else we can replace it by, n is greater than or equal to 5.
Using unit to show that n is greater or equal to 5.
Okay, so this emails n times n. What does that mean? If n is greater than or equal to 5, then I could write this as 5n, and that would be true. Which I could write as 2n plus 3n, and that would be true. That's greater than or equal to 15. Right, because n is at least 5, which is definitely strictly greater than that. Induction is getting too easy. Let's do another technique. I asked about this on the quiz. Minimum counterexample. What does minimum counterexample mean? What is this technique?
Show that
choose particular models are true and then say that other ones are false. So we choose from those other minimum ones to be false, and prove it's a prediction.
Right, so uses same technique we use to prove the well-ordering principle implies mathematical induction, i.e., to show Pn is true for all n assume it's false for some n. And so, because n is well ordered, there must be a minimum for which it's false. And then what you do is show this leads to a contradiction. So, I'm not going to add space. Show that 5 divides n to the 5th minus n for all natural numbers n using Jhevon counterexample.
Is this going to keep pretty similar? I mean, essentially what we used to show there's no largest prime number. Assume there was a largest prime number and showed that.
It's not quite the same. It's not really the same thing now. So basically the proof would go like this. Assume that 5 does not divide n to the 5th n for all n in n. Let n in n be the minimum natural for which this is the case. Right? So you usually start out like that. The next thing that you want to do is to actually show, you want to sort of get a minimum for n itself, right? So you want to say n is bigger than this number, right? So for example, you can say since since 5 actually divides 1 to the 5th minus 1, we know that n must be greater than or equal to 1. Right? And then you use this other trick, which is very typical to use. Introduce another integer, right? Call it k, where k is an integer, but k is of course, since n is greater than or equal to 1, k in this case has to be greater than or equal to 0 for it to work. Right? In particular, your k would be less than n, right? Which we're going to use that fact, right? Because n is the minimum for which it doesn't work, so we know for k it would work. Right? So, now we're going to want to get a contradiction from all this. This running out. So, what do you think we're going to do? We can say something like, then, if I look at m to the 5th minus n, right? Basically what I'm going to do is I'm going to show that 5 actually divides this guy, which is going to give me a contradiction, right? Because I'm assuming 5 doesn't divide. Well, if I plug in a k plus 1, what am I going to get? What's this guy?
K plus not k plus 2 n.
Minus k minus 1, right? Pascal's triangle one. Okay, so this is actually k to the 5th plus 5k to the 4th plus 10k cubed plus 10k squared plus 4k
You can pull out a k and k is divisible.
We don't know that k is
Or not.
divisible by 5.
No, k is divisible by 5.
I'll give you a hint. It's probably better to leave it like this. Now do you see what you can do? Right, this is really k to the 5th minus k plus 5 times, this is k to the 4th plus 2k cubed plus 2k squared plus 1 plus k. Now this is equal, this, right, k to the 5th minus k has this form, and k is less than m. M is the smallest for which this claim is false, which means for k it's actually true, which means this I can write as that. Since the claim is true for k. Right? The idea is m is the smallest guy for which it's false, but k is smaller than m, so it has to be true for k. Well then, that just gives us this guy. Which means 5 actually divides m to the 5th minus m. And we end up with a contradiction. So our assumption must have been in error. So this technique is called proof by minimum counterexample. So you pretty much assume there's a minimum counterexample and then show that that does make sense. So it has to work for everyone. Right, and this is very typical. You sort of introduce a new variable that's less than your m and use that to your advantage. You're going to show that it works for that guy and ultimately show that it works for n by doing this. One thing I'd like to point out with these guys is, with these problems, it's actually very typical that you'll need to verify more than one cases. So, for example, if I wanted to prove that 12 divides into the 4 minus n squared for all n in n, then this one would actually be a little bit tricky. So assume 12 does not divide into 4 minus n squared for all n in n, and let m in n be the minimum for which this is the case. Then let's do something similar. So let's verify for a couple of them. 12 actually divides 1 to the 4th minus 1 squared. So we know that m is at least 1. So write I want to actually go through the trial and error. So I'm gonna write what you would sort of assume and you do, and you realize it doesn't work, and then you come back and you try it again. Okay, so let's say we assume that n is at least 1, so we probably continue very similar to here. And so we want to go something like k plus 1 to the 4th minus k plus 1 squared. And I actually did that, and the answer was k to the 4th plus 4k cubed plus 5k squared plus 2k. Now, what was the problem with that? So if I continued very similar here, it works for 1, so I know it's at least 1, so I assume m is equal to k plus 1. Then I did this expression, which is this. The problem is, I can't actually factor a 12 out of that, right? Because there's a 4 here, there's a 2 here, right? So then what you do is that, okay, go back. Sure, it works for at least 2, right? So if I put also 12 divides 2 to the 4th times 2 squared, right? That's actually 12. So m is at least 2. And then you do a similar technique and you look at k plus 2, right? So I did this, and what I end up with is k to the 4th plus 8k cubed plus 23k squared plus 28k plus 12. And I still run into problems, because again, this guy is indivisible by 12, and this guy could make divisible by 12, but these two guys mess up, right? So basically, I went through this process a bunch of times, and it turns out that to actually get to something that I know is divisible by 12, I actually had to do it 6 times, right? Which can happen, right? I did it for 1, 2, 3, blah, blah. There was always a couple guys that was giving me trouble. When I get to the 6th time, the answer there was k to the 4 plus 24k cubed plus 215k squared plus 852k plus 1260. And at this point, I could write this as k to the 4th minus k squared plus 24k cubed plus 216k squared plus 852k plus 1260. Which, since I know it works for k, because k would be less than m, this guy is actually 12 times x. So the whole thing was 12 times x plus 12 goes into this 2 times. Plus 12 goes into 216 18 times. It goes into 852 71 times. And it goes into 1260 105 times. So this means you would have to verify up to n equals 6. Right? So minimum counterexample is sort of annoying in that way. Sometimes you need to get a lot of base cases out of the way, because before you can get a contradiction, you have to do a bunch of processes, which can be annoying, but it's one of the things I had to learn the hard way. Yeah, that's true. Let's redo a problem. Prove 2 to the n is greater than n squared. We actually did this. for all n greater than or equal to 5 by minimum counterexample. So now we can say since 2 to the 5th is actually greater than 5 squared, n is at least 5. So write n is equal to, I could do k plus 1, where k is at least 4. And then, if I look at 2 to the n, I just get 2 to the k plus 1. Which is 2 times 2 to the k, which is, at this point it's going to look very similar to the last proof. It's just the setup is going to be different. So this is going to be greater than or equal to 2 k squared, which is equal to k squared plus k squared. And using the same argument, we can show that k squared is greater than this. So that's what the proof would look like with that technique. Looks very similar, but the setup is kind of different. Again, there are cases where you might have to verify for several cases before you can actually make this work, but in this case it was fine. In this case, our k is greater than or equal to 4, so this you say it's greater than or equal to 4k, which is definitely greater than 2k plus 2, which gives you greater than 2k plus 1. Right now, I'll just introduce the last technique in this chapter. Should be able to pick up on it. It's called the strong form. Or the principle of strong mathematical induction or something similar. Given be a statement. And then if 1, P of 1 is true, and 2, So it's pretty much like induction, except you definitely need more than just the base case for you to get to the next guy, right? So to prove this guy, you'd have to basically assume that everyone before him would work, right? There's an alternative way to write that. So it's sort of like an induction mixed with a minimum counterexample. You have to prove several steps to get to the next step. Right? For your induction to work out, it turns out you need more than one cases. It's slightly similar to the proof I did with the subsets, where I had to prove the Morgan's law, where I had to prove that it worked for not only one set, but two sets, and then the rest were easy. So technically I use a strong form there. You can write it in this way. If one, P of one holds, and two, P. It's just another way to express it that conceptually might be easier. P of I holds for all then this guy will hold for all n, right? So assume it works for everyone from 1 up to a certain number, and then prove it works for the very next number. And that is actually proving it by strong form induction, right? So you need a much stronger condition to make this work. You have to check a bunch of things, right? And that works on like this. Try to do this example. So something like that you might need strong form for. Did I do an example of? Right, so here's an example. You can actually prove it by induction. There are other ways, but you'd use strong form induction if you're using induction. You'll notice that for this term, to figure out what that term is, you actually need to know what the previous term is, and what the guy before that is, and what the guy before that is, right? You'll actually need 3 steps into the past, right? Not just 1. So to prove this by induction, it's not good enough to just prove the base case, because at best you can just prove the guy that came before. Here we're going to need 3 guys that came before. So you have to verify at least 3 cases to make this work, maybe more depending on how incontractable it is, and prove that your formula works in general. So you can pick up with that example tomorrow, and we will continue from there.